All right, so we continue off our discussion of system software, still on lecture series number 5, which is computer software. In this particular unit, we discuss language translators. And I thought we'd start off our discussion by reminding ourselves of this whole notion of high-level languages or high-level language notations versus low-level language notations. And this really came up when we had a broad discussion of how computer software is created. We made mention of the fact that contemporary computer software is typically implemented using so-called high-level programming languages, specifically because they highly abstract the machine language that the computer or the hardware will typically understand, making it much more efficient and effective to actually create these software programs, right? And really, it turns out really that if you think about it, if you have a programmer that writes a high-level language with the express goal of eventually having a computer system be able to interpret that high-level language, right, then it goes without saying that you need some component somewhere that will be able to easily convert this high-level language into a form that the computer hardware will be able to understand, right? This is fundamentally the idea behind a language translator. The sole purpose of language translators is to be able to convert a program that is written into one notation into an equivalent different notation. In this particular example, you'd be converting a program written in a high-level language into its equivalent low-level notation or low-level language, right? And it turns out really, it's kind of funny, really, kind of chicken-egg problem, but it turns out that language translators are themselves computer programs, right? And so they work to, as I mentioned, they work to convert program instructions that are written in one language into an equivalent different representation, right? There's a whole broad spectrum of these things that are referred to as language translators. Common ones that you typically find in literature include assemblers, disassemblers, interpreters, compilers, and decompilers. An interesting thing about these examples that have been enumerated here, if we look at assemblers and disassemblers, for instance, is the fact that a disassembler will actually do the opposite of an assembler. And this makes sense, right? If you have a piece of software, a computer program called a language translator that enables you to translate a high-level language notation into equivalent low-level language notation, then it makes sense that you have a different translator that is able to do the opposite, right? This is exactly what assemblers and disassemblers do. So your assembler, such as MIPS assembler, for instance, will convert assembly language programs written using MIPS into a form that a computer will be able to execute, right? Machine code. And a disassembler will actually do the opposite, convert the machine code into assembly language notation. So I thought would actually focus our discussion of language translators on compilers and interpreters, specifically because most of the literature that you typically come across will place an emphasis on compilers and interpreters. One of the reasons this is the case is because most of these so-called high-level programming languages that are used to write contemporary software programs would typically fall in these two broad categories, right? So you have a class of programming languages, high-level programming languages, which are compiled, and another class of programming languages which are interpreted, right? And really they serve to perform a similar function, and that is conversion of high-level machine instructions into a form that the computer hardware will be able to understand. The only difference is in the way in which the translation is performed or conducted. With compilers, what typically happens is the high-level program instructions are converted into an equivalent machine executable program, right? So the outcome when a compiler is used is a program which can then be executed by the machine. Interpreters, on the other hand, will typically translate the statements associated with this high-level programming language, right? So this is done instruction by instruction. So let's say you have a computer program written using an interpreted language with 5 lines of code. What an interpreter will do is it will convert each of those statements one at a time into equivalent machine code, right, which can later on be executed by the computer hardware, right? Again, in the case of compilers, the outcome or the output is a machine executable program. In the case of interpreters, the output are individual instructions that are executed by the computer hardware. Another way of looking at this is that in the case of compilers, what you're dealing with as output is what you're dealing with eventually is a program execution is what happens, but with interpreters, it's execution of the individual statements essentially. In terms of examples, really, there's a ton of examples out there, but classic and common examples that you typically find in literature for interpreted programming languages are things like PHP, JavaScript, Perl, and Python. Right? Examples or classic examples of compiled languages would be C and C++. Not quite sure if C# is also a compiled programming language. It should be. Interestingly enough, though, you have certain languages that would typically fall in between these two broad categories. So languages like Java are classified as being a hybrid of the two. Right? But key takeaway point here is we're just looking at examples of interpreted languages. We're not really interested in the gory details of why Java is considered a hybrid programming language. All right, so again, just to try and provide an example of a compiled and interpreted language, we'll start with a compiled language. This is Java. I know I said it's a hybrid, but just using it as an example here. The top part of the program here would be the instructions that a programmer would typically come up with, right? So you write a simple program here that will enable a user add 2 numbers, right? Or add 2 and 3, very simple program. You use the Java compiler, right? To compile this into a form that a machine will be able to understand. Yeah. So once you run Java onto this particular source code written by a human being or a programmer, the outcome is going to be an equivalent notation called bytecode, right? Java bytecode is obviously the output of running Java compiler on source code, and then you can use this Java, right? This Java command to be able to execute the output coming from Java, right? And incidentally, what would typically happen when you're running Java applications is you'd need what they call a Java virtual machine, or the JVM, which simulates the computer hardware essentially, right? So using that as an example, the JVM would play the role of your computer hardware, right? So it would, the JVM would execute the output of the Java compiler, right? So compiler results in an executable program that is run by the computer hardware. In this case, we're simulating the computer hardware in the form of the Java virtual machine. Right? In terms of interpreted languages, The situation is completely different. No need for you to actually derive an executable program, but rather what typically happens is each individual instruction associated with the source code is executed one line at a time, right? So the top part of the screen here has a very simple example of Python code, which does more or less the same, it does the same exact thing as this Java program, adds 2 and 3, then gives you the output. You notice here that for us to be able to get the result we want, all we have to do is use the Python interpreter, right, to execute this program one statement at a time. And then we get this same result as we are getting from our Java program. Key thing here is just showcasing the example. I'm trying to emphasize the fact that with a compiler, it's a two-step process. You generate a program executable, right, an executable file by using the compiler, right? So the compiler is used to run or to generate the program executable by using the source code as input, right? And then the machine will be able to execute the actual executable program generated by the compiler. With an interpreter, what typically happens, or what happens is each statement associated with the program is executed one line at a time, right? The result is typically the same. You typically come across this as you're reading up, the fact that for the most part, compilers are much more efficient than interpreters, simply because the execution by the hardware, by the computer, is done on the result which is already in a form that it understands. In the case of an interpreter, as the program is being executed, each statement has to first of all be converted into a form that a computer understands, right? All right. Again, just to recap here, this whole notion or idea that in the case of the compilers, the compiled languages will typically be deployed as executable, right? But in the case of interpreters, you have a situation where you typically would need an interpreter for you to be able to execute the programs, right? I guess you could view that as being one of the drawbacks of an interpreter, right? If you write a program if you write software using an interpreted language, you need to make sure that the person who's going to use that piece of software needs to have access to an interpreter that they're going to use to execute that program. In the case of a compiler, you can actually compile the piece of software and just ship the program executable to the end user, right? So think of these program executables as the equivalent of what you see when you download software and it's a .exe. You just double click it and then you're installing it. You're installing it because you're able to do that because what you get as a resulting output is a program executable, right? If someone writes a piece of software using Python, they would probably tell you to say, before you can use the program, you need to make sure that you install the Python interpreter. In certain instances, the interpreter is potentially packaged together with the software so that as you're installing the piece of software, behind the scenes, you also install the interpreter, right? All right, and then just quickly here, I just thought it would be important for us to highlight something that is going to come our way very soon. This is when we discuss MIPS assembler, right? During our discussion of computer architecture, this would be a very familiar sight, right? So when you write MIPS assembler or MIPS assembly language programs, this is the sort of notation that you work with, right? Once you write this piece of assembly language program, you then use an assembler to convert it into a form that the machine will be able to understand, so ones and zeros, right? Again, the key takeaway point here with language translators is what you're doing is just converting one representation into a completely different but equivalent representation. Why? because it might just turn out that the entity that would want to use the equivalent representation would need that piece of source code to be represented into a form that it's able to understand. Right? In the case of an assembler, the machine would only be able to understand binary code or ones and zeros. The program, on the other hand, will write the assembly language program using assembler or assembly language notation like this. Okay, so in the next lecture series, we get to discuss firmware and operating systems. Thank you very much, and I'll see you in the next unit. I think I'm tired, which is why this is a bit sluggish in this lecture series.